Good morning, everyone. So today we are beginning a new chapter in the course on deep learning. This chapter is titled Monte Carlo Methods. We've encountered sampling as a topic within deep learning, but this is looking at it in a broader way. We begin by discussing what is a Monte Carlo algorithm and contrast it with another type of algorithm called a Las Vegas algorithm. A Monte Carlo algorithm is based on some randomness, as the name indicates. It's as if we are dealing with a casino, that we are getting some random samples. As in a casino, the returns would be random. So in a Monte Carlo algorithm, the goal is to compute something. Some value is needed, some classification, the class is to be decided. Regression value is to be determined. That is, for this input, what is the output? A Monte Carlo algorithm will not always give you an exact answer, but it will give you a fairly good answer, an approximate answer. And the amount of error this approximation has is random. It's variable. It's not like it's going to be very large amount of error. We can bound it. It's typically based on obtaining some samples and estimating the value as opposed to exactly computing the value. So a Monte Carlo algorithm has that flavor that it will give you an approximate answer with and also within a given fixed amount of resources. So if you say, look, I cannot spend a lot of time on this computation, I need an answer within so many seconds or milliseconds. And it can have a very small amount of error. In the sense, instead of answering 3.0 is the answer is something like 2.999. That's good enough for us, that it's close enough, but there's a bit of error there. It's 0.0001 is the error. It could be smaller or larger. A Monte Carlo algorithm gives such an answer. What about a Las Vegas algorithm? It's just another type of algorithm to obtain answers. A Las Vegas algorithm is guaranteed to give you the correct answer. The correct answer of 3.0 is the answer. But the amount of time it takes to compute that answer is variable. So it can take a very short period of time or it can take a very long period of time. So we're doing a trade-off here between time and accuracy. And in the case of Las Vegas, in the case of Monte Carlo algorithm, the time is fixed. So it's going to be returning an answer within a known amount of time, but the answer may not be precise. So we can say these are two styles of computing something which is typically an intractable problem. That is, the reason we are resorting to a Monte Carlo algorithm is that the exact computation is intractable. Intractable means the amount of time taken is exponential with the size of the input. So sometimes even the size need not be very large, and still the amount of time is impossibly large. So we encounter this situation often. As for example, when we discussed Markov models or Markov networks, we talked about the partition function being a sum over all possible values of all the variables in the network. And the number of possible variables in a deep learning network is quite large. And the number of possible values they can take also can be large. Actually, it doesn't need to be very large because of the exponential nature of things. So under these conditions is when we would be resorting to a Monte Carlo algorithm. So today's topic is about the prevalence of Monte Carlo algorithms in machine learning and deep learning. They are used not only to compute the partition function. We talk about sampling even in some very simple circumstances in machine learning, such as mini-batch for determining stochastic gradient descent. We say take a sample, a subsample from the training set, and we run it through the network and update the parameters. And so those are all obtained by sampling. It's not an intractable problem, it's a tractable problem, but we need to get samples there. And more commonly, the intractable problems are in inference using machine learning or deep learning algorithms. That is, for an input, what should be the output? What is the output? And that computation may involve like determining the probability distribution for the output. Like what are the probabilities of all the classes, for instance, in a supervised learning problem? And that inference may involve marginalizing out the other variables, which could be the hidden values, and summing over all their possible values again is intractable. So these are the kinds of problems that motivate looking into sampling. And so we will look at what are the methods of sampling. We've already seen something called Gibbs sampling, but there is another method that is commonly used unless you are in a very specific setup where Gibbs sampling is the right choice. We will look at a method called importance sampling. And that is a technique of using a simpler distribution than the one at hand, sampling from an importance distribution and from a proposal distribution and determining its importance in computing whatever we're trying to compute. So we look at a specific technique called importance sampling, and after that go back into Gibbs sampling and where would these be appropriate. So that's the range of things. So we begin with Monte Carlo methods, compare it with Las Vegas methods. Then we will talk about importance sampling, and then we go to what are called as Markov chain Monte Carlo methods. So at this point, I'll share the slides for the class. Okay, as the first slide indicates, this is about Monte Carlo methods in deep learning. And the topics that we will cover today are 1 and 2, sampling and Monte Carlo methods. And then we will also cover what is importance sampling. And I don't think we'll have time enough to go to topic number 3, which is Markov chain Monte Carlo methods. Once again, a look at Gibbs sampling and would we use that instead of importance sampling. And then there is an important topic, number 5, which is mixing between separated modes. This is an issue that relates to mode collapse. So let's begin with Monte Carlo versus Las Vegas algorithms. Just to fix these concepts in mind, I have a picture on the left of Casino di Monte Carlo, which is the famous casino in the city of Monte Carlo, where there are lots of casinos where you have these slot machines that one can gamble. On the right-hand side is the famous Las Vegas Strip, which has got dozens of casinos and with all famous landmarks being shown with lights and so on. So both are places for gambling. Turns out gambling is a good thing in machine learning. Turns out we use samples, random samples, to compute things that cannot be done in an ordinary way. So once again, Monte Carlo algorithms return answers with a random amount of error, right? That's the example of 2.9999 instead of 3.0. For a fixed computational budget, Monte Carlo algorithms provide an approximate answer. So you can only take so much time, so it will give you an approximate answer. A Las Vegas algorithm, on the other hand, returns an exact answer. It will give you 3.0, but the time used to compute the answer to be 3.0 would be random, right? So it need not be a fixed period of time. It needs more and more time to consume. In a way, if you kind of open up how many samples you're going to be using for a Monte Carlo algorithm, it becomes a Las Vegas algorithm because you can keep on adding terms and becomes an exact answer. But the amount of time taken may vary. Monte Carlo algorithms are fast, but only probably correct. So they quickly give you an approximate answer, which is usually what we are happy with. Las Vegas algorithms are always correct, but probably fast. We design them to try and give us an answer as quickly as possible, but it might take a variable amount of time. So let's now distinguish between inference and learning. So inference let's begin with learning. Learning is beginning with historical data. So we have a data set and we would like to use that data set and use some algorithms to determine a model. Right? So learning is to determine a model from samples. Inference is when I give you some new data, we want to use the model to make a prediction. For instance, historical data could be supervised learning data with inputs and labels. We construct a model, whereas an inference method would actually take that input data and figure out what the label should be. Many machine learning problems are difficult. We cannot get precise answers. We can use either deterministic approximate algorithms or Monte Carlo approximations. So we're saying some machine learning problems are difficult. And the way to infer the right answer would be to use an approximate algorithm that's famously known as variational methods. And or we can use Monte Carlo. Variational methods, for example, we replace the particular distribution that we're dealing with by a simpler version of it. And then we use that to do the inference. That would be an approximate algorithm. Whereas a Monte Carlo approximation would be a sampling approach to the same problem where we don't approximate the task, but we actually take samples and use them to determine the answer. And both approaches are used in machine learning. So the role of Monte Carlo methods. So many machine learning algorithms are based on drawing samples from some probability distribution and using these samples to form a Monte Carlo estimate of a desired quantity. So we are looking for an answer. What is an example here? Even the simple inference problem, let's say an autonomous driving algorithm. It is trying to figure out what should be the acceleration, the gas given to the automobile, petrol given to the automobile, or what should be the turn of the steering wheel. We are looking for an answer, and it is trying to figure it out based on the inputs, which is the let's say the vision inputs coming in from the cameras and the sonar and so on. So we want to take those inputs and we need to calculate the exact value for the steering wheel and the gas pedal. And we want a quick answer to that. So one way to do it would be to generate some samples from the model that we have and then quickly compute the desired quantity. All right, again, the question, why sampling? Many machine learning algorithms are based on drawing samples from a probability distribution. So we're saying we've got all of these distributions determined, We saw how this was possible. Like in an unsupervised learning, a restricted Boltzmann machine captures a probability distribution. And to approximate sums and algorithms during learning, and it could be a tractable sum, subsample for mini batches. For instance, we take a mini batch and we compute the derivative of the loss function over the mini batch of, let's say, small m number of samples, and we compute the derivative as a loss function over the m samples, and that would be a derivative with the mini batch of m samples, and we could use that to update the parameters, right? Or it could be the gradient of the log partition function of a restricted Boltzmann machine. So where that also ends up saying over a set of samples, capital M, determine the derivative. So those are all tractable situations. An intractable sum is of the kind like in a Gibbs distribution. We have to calculate z, or the partition function z of theta, and that quantity is summed over all possible values of all the variables x, and that is an exponential quantity. You have to go through all possible values. Even if it is binary valued, it's still the order of 2 to the power of number of variables you have. So it could be an intractable sum, and it's not possible to sum over all the possible values, so we want an approximation. So we're saying that sampling is needed for determining tractable sums, sampling is needed for intractable sums, but sampling may be actually a worthwhile end itself. It's not just a means to compute something. So we want to train a model so that we can sample from it. Here is some celebrity faces, and there is a style GAN which generates all these faces. They're all generated models, samples from the distribution. They're not necessarily real faces, but they're just samples. And we may want these samples, sample hairstyles or sample styles or whatever it is. We want some samples, and that actually could be the goal. So samples could be a means to an end or an end in itself. So we have two classes of methods here. One are simply Monte Carlo methods, that is based on samples from the distribution. And a method that we will look at is called importance sampling, a particular method, that's the name of the method. It says importance sampling is an approach which says take samples from a proposal distribution, and then we'll attach some importance to it. How good a sample is it? So we're talking about the goodness of a sample, which is also the importance of the sample. It is used in neural language models with large vocabulary. Importance sampling is actually used in language models, particularly with a large vocabulary or other neural nets with large number of outputs. When you have a large number of possibilities, the number of computation may be large, so importance sampling is useful. And or in a particular generative model called a variational autoencoder, or VAE, we are to compute a log likelihood, and that log likelihood involves estimating something, and that is done using importance samples. The third example given here of importance sampling is gradient and stochastic gradient descent, where cost comes from a few misclassified samples. So in stochastic gradient descent, we are determining the cost or the loss, and it's usually triggered by misclassified samples. These are not right, so we got to make a change. And sampling difficult examples reduces variance with gradient. So this is saying that without having to deal with all difficult examples, sampling them can be used. MC is another type of method which stands, now MC and MC stand for different things. This says Markov chain Monte Carlo. It so happens that both of them have these symbols M and C, Markov chain Monte Carlo. Gibbs sampling is one of those kinds of methods where the next sample depends on the previous sample, which is very different from the other simple Markov chain methods where the samples are independent. Markov chain Monte Carlo, they are dependent, and it actually is a chain. And as long as we wait long enough for the samples to reach a steady state, we get good samples. And where does that get used? Is inference in RBMs. We actually saw that in restricted Boltzmann machines. We are trying to do inference. We're trying to infer the value of the hidden nodes, for instance. And a stacked set of RBMs, which is referred to as a deep belief nets. So there's a role for each of these. So we would like to have an understanding of what is importance sampling. And once again, Gibbs sampling, which we have seen already. So some of the basics of Monte Carlo sampling is that a sum or integral is intractable. Right? Machine learning involves both differentiation and integration. Differentiation because of backpropagation, that's what the entire backpropagation learning is all based on. And integration comes about because we are usually using some kind of application of Bayes rule, which involves determining a distribution. To determine a marginal distribution, you have to sum out all the other variables in a joint distribution. So you have essentially a summation, or if you're dealing with a continuous variable, it becomes an integral. And there are exponential number of terms here. The number of terms in the summation is exponential, and there is no exact simplification available. Right? Occasionally, we have some very nice exact simplification available for a summation. Right? So we approximate using Monte Carlo sampling. And the major point here is that we view it as an expectation under a distribution. So if you're saying sum over all these possible values, then we say that is very similar to what exactly happens when we're trying to determine an expected value of a distribution. And we got to remember what is the definition of expected value of a distribution. It's basically the average value. If we say here is a variable that is a normal distribution, and let's say the the normally distributed variable is x, then we say what is expected value of x? We say expected value of x for a normal distribution mathematically shown to be the sample mean. That is, you take a set of samples from the distribution, add them up, divided by the number of samples. That is the value, an average value. So this is the idea of this use here is when we are looking for an approximation, we can view it as an expectation under a distribution. And an expected value is approximated as an average. So the expected value of x is mu, and mu is approximated by sum of the samples, or the average of the samples. So this kind of summation occurs often in machine learning. This is a very simple case of restricted Boltzmann machine, where we're saying the marginal distribution over the visible values can be written as the marginalization of the joint distribution. The summation of P of h comma b. If you have a joint distribution determined by the weights, for example, in RBM, we'd say, well, you know, the W's are all known after you finish training it. And if you're asking the question, for a given image as input, B is visible values, what is the probability of this? This says, well, you take the joint probability distribution. How do we know the joint probability distribution? We know it because we've got the energy formulation and for which we know all the W's and all the bias parameters. So we know the joint probability distribution. It says to determine P of V, you need to marginalize out the H variable. That's why we get the summation of H. And it says, note that PH comma V can be written as P V given H times PFH by Bayes rule. Right? And in the case of an RBM, we can argue that PV given H can be obtained easily. And also, if you know the distribution over H, you can use these two together to determine PV. So there is a summation. When the sum integral cannot be computed exactly, Monte Carlo methods view the sum as an expectation. If we have a large number of possibilities, then we view that as an expectation. So let us show this line of thinking. A summation is treated as an expectation, and once you treat it as an expectation, that can be approximated by an average. So let's say we wanted to compute something like this: S is equal to summation over x p f x f of x, right? Or here is the continuous version of it: integral of p of x f of x dx. So it says that is what we want to compute, right? We just saw in the previous slide an example of two probability distributions being multiplied out. One is a conditional, the other one is a marginal. Then we rewrite that expression as an expectation, and we say that S can be written as an expected value of f of x, with the constraint that P is a distribution. So we just saw that the expected value for a distribution can be written as an average. So this says, if you are trying to compute something like this, S is equal to P of x, f of x, summation over all x, that is exactly done by this quantity here. I should say exactly it is. It's approximated by this, which is Sn hat, which is you have some n number of samples and it's an estimate, is 1 over n of f of xi, and the xi's are the samples drawn from that distribution x. All right, so that's what you need to do. So this is saying we needed a summation, we rewrite that as an expectation, and then we say we can determine the expectation as a sample mean. So this is what's going on here. So we say P of x is a distribution under which we are drawing it. So now we should ask two questions. Justification of the approximation. How does this value approximate the expected value, the sample mean? It is justified by two properties, statistical properties. We are just talking about basic statistics here. The estimator Sn hat is unbiased since the expected value of Sn hat is equal to S. So we can show that this is an unbiased estimator. As the number of samples becomes large, this becomes equal to the sample. So this is an unbiased estimate, the expected value of that quantity. The law of large numbers, which is another famous law, which says if xi are identically distributed, then the average converges to the expectation. So there is good reason to see why the sample mean converges to the true parameter. Right? Just think about it like a Gaussian distribution, normal distribution. It says the sample mean of the values converges to the true mean as the number of samples increases. Right? So that can be shown mathematically. And we're saying that this in a more general way. It need not be a Gaussian distribution, that we have these general properties. Another thing we want to know is the variance of the estimate. So think back on what we just said about Monte Carlo algorithm. So a Monte Carlo algorithm gives you an approximate answer. You ask the question, well, how approximate is it? Let's say we are trying to determine how much the steering wheel has to turn or how much acceleration has to be put on the gas pedal in the car. We want to be sure that it's not going to be very wrong. So we have to ask the question, how wrong can you be? Well, let's say, so then we look at the variance. Consider the variance of Sn hat as n increases. So it says, what is n again here? N is the number of samples we are taking from the distribution. We got this box, which is the deep learning box, which is a model which has learnt it from all the driving experience you have given it. And we are now faced with a new scenario. The car is driving on the highway, and we're asking how much should I turn the wheel and how much gas should I give? Give me an answer quickly. And this is what it's trying to determine from sampling the model. There is a model here inside the box of the world, and we're drawing some number of samples from here and using that to determine the answer from that probability distribution. Probability distribution is capturing all the variables involved. And so we're saying, can you give it? I can either give you an exact answer, that would be a variational approximation, a deterministic solution, I should say. This is a non-deterministic solution based on samples. So it says consider the variance as n increases. It says variance of Sn converges and decreases to zero if the variance of f of x is smaller than a certain quantity, and the variance is expression is given here where n occurs in the denominator, showing that as n increases, the variance decreases. So the result tells us how to estimate error in a Markov chain approximation, equivalently expected error of the approximation, and compute empirical average of the fxi and the empirical variance to determine the estimator. And this gives it relates to the central limit theorem. The distribution of the average is a normal distribution with mean S and variance. This allows us to estimate the confidence intervals around the estimate using normal CDF. So the point of it is, if we can use as some set of samples, we can use the size n of the samples, and we can actually give a confidence interval saying, this is the answer within plus or minus 0.05, something like that. That's a confidence interval. So it's possible to do that. So we are saying the answer to the question of the steering amount of steering to be done or amount of gas is here is obtained from the model with samples, and we can say that this is the answer which is good within plus or minus something, and that is dependent on how many samples you take. Above method relies on our ability to sample from a base distribution PFX. It says, well, you got to be able to sample from the distribution you have modeled. And the sample from that distribution is not always possible, because we're talking about a very complicated distribution. Let's say you take the pixels, even the faces, we're talking about a very complex distribution. And we are asking for, give me some sample faces. And that's a complex distribution. When it is not possible, an alternative is to use importance sampling. So we have to study a method called importance sampling. How do we generate samples? A more general approach is Monte Carlo Markov chain, which again is exemplified by Gibbs. Okay, we need to go to the next set of slides, which I will try and make sure that I share. Okay, are you able to see the screen, importance sampling? Okay, I think I've shared it now.
Yes, sir.
Okay, very good.
Thank you, sir.
All right, important sampling. So sampling is a very big topic. Um, what is our goal here is this is still our study on deep learning, and we want to learn the essential methods. And we already saw ancestral sampling, fairly a simple method for a directed graphical model. We also saw Gibbs sampling for an undirected model. But there's one more method we should keep it in our arsenal. And we'll say, where all is it used? Where is importance sampling? And there is also like a dozen different methods, basic methods exist. There is also something called rejection sampling, which is actually a simpler version of importance sampling. So, but anyway, we want to use importance sampling. We want to learn importance sampling because it is used. So if one claims to know the techniques of machine learning, then one needs to know some sampling methods. Importance sampling is one of them. Which reminds me of a cartoon I just saw yesterday. Somebody posted it on Facebook. That certain topics are complicated, that you got to learn the method. And here is a person who goes to a bookstore and is trying to buy 2 books at the bookstore. And the title of the book is Mathematics for Dummies, right? The title of the book is Mathematics for Dummies. The sales agent takes them and runs it off on the cash register and says, each of these books is $14.99, right? So it's $14.99 for one and $14.99 for the other. And he says the total is 50, right? So that's what the salesman is telling the customer who's buying a book, Mathematics for Dummies, right? So the reason I found that relevant is mathematics requires a certain amount of ability, right? That 1499 plus 1499 is far from being equal to 50. And similarly, machine learning is also a subject. One cannot say it is. Can we have a version of machine learning for dummies, right? The answer is, well, there is a certain amount of expertise you got to have. It is difficult to teach or know machine learning without a certain amount of mathematical expertise. So one has to have some rudimentary knowledge of things, like such as 1499 plus 1499 is much less than 50. One needs to have the same kind of knowledge. Well, here we're talking about a number of different techniques. We've talked about chain rule of calculus, right? All kinds of mathematical techniques. And now we are on to sampling methods from probability distributions. And you can't say that can I do without sampling? Well, that is an essential part of inference in machine learning. You got to learn something about sampling. So you have, that's part of it. Anyway, important sampling is one of these. All right, we're into topic 2 here within Monte Carlo methods. We have just talked about sampling in Monte Carlo methods, where we talked about the nature of sampling and the nature of tractable algorithms going from sums to expectations to averages. That's what we did in the last set of slides. And now we'll talk about importance sampling. So in importance sampling, this is actually more about sampling in general in machine learning. And importance sampling will be just a method for it. I cannot hear you well. Are you saying something? Let me, I cannot hear you at all. I put you on max volume here. Yeah, go ahead. Yeah. No, there is something wrong here in terms of the sound quality. I cannot hear what you're saying.
What? What?
There's a lot of crosstalk. Yeah. Okay, I'm going to.
Sir, you have unmuted everybody, no? So that's why there's a crosstalk from the home.
Oh, okay, okay. All right.
So you mute everybody, sir. I think they are not trying to talk to you.
Oh, I
They are
see.
talking on their own.
Okay. Okay. All right. Selvi, I'm going to keep you unmuted because I have no
Okay,
problem.
sir.
All right.
I'm also in the office, so something
you're in the
might be
office, you're in
disturbing you also.
quite
Yeah.
nice setting. Okay, there's no other problem. I think CSA 250 had
Yes,
some
sir.
crosstalk going on. All right.
Okay.
So, Selvi, do you know the question? What it was? No.
I
Okay.
don't think it was a question, sir. I think
Just
it was crosstalk only.
Just some crosstalk. Okay, fine. All right.
Okay.
So we are on to import sampling, and we are trying to determine this. S is equal to summation over x p of x times f of x. So we can say that is of the form expected value of f of x. That's the definition of it.
Sir, please put slideshow, sir. The equations are not visible.
Oh, you're not visible. Oh, no. Okay, all right.
Slideshow.
Slideshow. Okay, let me just go to slideshow. Okay, good. So slideshow. Okay, now we can see it, right?
Yes,
Yeah.
sir. Thank
Okay.
you, sir.
Excellent. All right, now the equations are better visible. So we got this equation S is equal to summation over all of x p of x times f of x. And that is basically the definition of expected value of f of x. We're simply asking the question, what is the average value of some function of x under the probability distribution P? If that f of x was simply equal to x, it would have been the expected value of x. What is the mean value? That's what we'll be saying. So that is the kind of problem we're going to be facing in many situations. Where would we be facing this situation? Here is an example on the right-hand side. Example. Let's say we have visible nodes and hidden nodes in a deep learning network. And we're asking, what is the probability of this observation here? V is the endpoint. It says, well, if you know the joint probability P of H comma V, that's what the model would be doing. It would have modeled that for based on the set of weights it has got, right? So it knows the distribution for any combination of H and V. It says you have to sum over all the values of H, calculate for each of them what is P of H comma V, add them all up. The other alternative is actually multiply out H comma V by the product V given H times P of H. That might be the easier way to know that. For an RBM, those are the things that are known, PV given H. There are some simple expressions for that. So we are talking about a summation of this kind of quantity. So should we be taking the first one as a distribution or the second one as a distribution is a question. So we're saying, first, which part of this is called as the integrand. What occurs inside the integral is called the integrand. Okay, integrand. Has a role, which part of the integrand has a role of the probability P of x, and which part has the role f of x. So which do you regard as which? And sometimes this is up to us because both of them happen to, one is a conditional, other one is a marginal. And there is no unique decomposition because P of x times f of x can also be written as some P of x times f of x with Q of x in the numerator and in the denominator. And we are saying, well, we can then sample from Q and average this quantity. Isn't that interesting? Instead of sampling from P and averaging over f of x, we're saying we can sample from some other Q, which isn't even part of this picture. Originally we were looking at S equal to summation P times F. Now we are bringing in P times F is equal to Q times P times F divided by Q. And bringing some Q, and we're saying go and sample from some other Q And from that distribution, you average the quantity that you're looking for. That's the clever idea here. Q is the idea, it's called as the proposal distribution. All right, so now we're talking about difficulty of sampling from P. So we kind of resort to this idea that drawing samples from P may be impractical. So we end up sampling from a Q. So let's take a look at the simple example. The true P has this multimodal distribution here on the left side, the blue curve. And we can imagine a deep learning network to have complicated distributions, which are not nicely normal. And then we are imposing on this bimodal distribution. Let's consider a simple distribution, which is normal. And we call that as our Q. The P is the bimodal blue one, and the Q is the dotted normal. And we refer to the dotted one as the proposal distribution. And we say, well, we're going to take samples from that Q, and we are going to keep that sample or not. In rejection sampling, it says, don't keep that sample if it's a particularly bad sample. Let's say we got a sample in this normal distribution from over here at the bottom of the green line here. And we say that is not a good sample. Why do you say that's not a good sample? Is we somehow measure this red quantity here and then the green quantity here. And then we say, well, this is a rejection area. This sample doesn't look like it suits our distribution very well. Throw it away. We only keep those samples when they kind of look like this distribution. And we throw it away if it doesn't. And how do you figure out whether to accept or reject? Well, this right-hand side figure helps do that. The true distribution is this P, and there is some version of it, K times Q is this blue one here. And this says the goal is to determine if the sample falls such that the corresponding sample in the proposal is in this gray area. Right? So how do we determine that? It says there is a way of doing it. Generate two random numbers, Z0 from QZ, U0 from the distribution, 0 to KQ. If this pair is a uniform distribution under the curve, etc., etc. So there is a way of doing rejection. So this says generate from some simple distribution and then check whether this is a good sample or not, and then you can use that. Importance sampling also relies on a proposal distribution where samples not matching some kind of conditioning are rejected, but all samples are retained. So rejection sampling keeps on throwing away samples, which is actually can be a problem because you're mostly throwing away all the samples you generate. Whereas the importance sampling says keep on generating samples, but associate an importance with every sample. This is just like going around taking samples of the population to answer some question, right? That's what we do. Sampling. We want to know what their opinion is, and we are asking 1,000 people what their opinion is. And of course, we got to choose them as a truly random sample to be representative of the population. But if they have some way saying after you obtain the sample, is this a good sample or not? And we are saying, no, this is not a good sample, or associate a weight with it. But some people have more weight and some people have less weight. And how do you determine the weight? It is determined by the original distribution from which you generated samples from and the true distribution. That's what importance sampling is about. So how do you determine the importance? Is samples xi from a simpler distribution Q, right? This red one is the true complicated distribution. Green is the simple one, and we are trying to estimate the value of some function f, right? So we're trying to do, what do you mean estimate? In the sense, what is the mean value of this particular function here over all possible values of the samples here? For all possible values, what is the average value of that function of x? Not simply x, it's f of x. So we are saying that is done by f of x times p of x d of x. And we're doing some simple algebra here, multiply and divide by q, right? I can introduce that q here. And then what we are doing is determining this p of x divided by q of x times f of x. This is now we were converting that into a summation over a set of n samples here. That's the converting the expectation into an average value. And we saw in the previous set of slides that a sample converges to the value you're looking for. And so this is saying, take the samples x, determine the f of xi, but we're going to associate a weight associated with that sample, p by q. So samples are weighted by the ratios r sub I equal to pxi or q sub pxi. These are called as importance weights, which corrects the bias introduced by the wrong distribution. So we have a distribution to sample from, but we have gone about getting samples from something else. So we say there's a bias here by that distribution, and we're saying, can you correct the bias by not considering every sample to be equally important? So this says it's a better way to compute these integrals or the summations than rejection. And it says reweigh the samples in a principled way. And it says expected value of f of x with these manipulations here, multiply, divide by q, and we refer to this p by q as a w. So this says this expected value is 1 over m f of xm times w of xm. So this is the weight. So we now bring in the idea of importance. The w is the importance of the sample. And here's a specific example of sampling, and we are bringing in a Q here. It's a very simple case. Let's say we had P as the original distribution we want to work with. We're working with Q as a uniform distribution here. It's flat here, right, in this region. And we are actually computing the ratio between P and Q here by superimposing P and Q, which tells us the weight associated with it. And then we say the distribution, what you're trying to estimate is simply the sum of these weights, which is the ratios here. And what are we doing here? This is as if we are trying to determine some probability of E when you have a joint between E and Z. And it is written in terms of a conditional here, and then the summation comes in. So basically, we're using weights here. So this example shows a complicated Gaussian itself is called a complicated distribution. The proposal is uniform, and this is the ratio of the two. This is how we compute the samples, and then we generate samples from this uniform distribution. And we have a weight associated with. I suppose it attaches a high weight to samples coming in the middle here, low weight to samples that kind of go far away here, based on the ratio of the two. So that's the idea of importance sampling. This is about dealing with intractable PFX. If the PFX is intractable, we just saw in the previous slide, P of x was a Gaussian. But what if this P of x, the true distribution, is too complicated that I cannot generate a probability associated with that, which is a fair situation. And let's say we are dealing with a Markov network or a deep learning network which models a distribution as a Gibbs distribution. And so we can deal with it as an unnormalized distribution, P tilde of x. It becomes a true distribution. only when you divide it by z, or the partition function. So it is not a true distribution, it's an unnormalized distribution, simply based on the factors, that's the weights between variables. Can you work with only those things by ignoring it as a distribution, but only knowing the unnormalized distribution? This says, well, yeah, there is a method called unnormalized importance sampling, where the weight is determined by the unnormalized p, that's p tilde divided by q. Q is something, it's up to you. You choose whatever you want, a Gaussian or a uniform. And the only thing is p tilde represents what the model is telling you. Then it says that expected value of the weight is given by this particular summation here of p tilde, and it's given as the weight alpha here, and said expected value of x of f of x is has an alpha term coming into play, and it is saying that can be re-expressed as a ratio here. So this says, therefore, we can determine expected value of x. So what is the expected value of f of x? We know that expected value is the step before the averaging, right? So we're going from the summation that is needed to expectation to the approximation. And so that quantity now is being written as summation x. These are the samples, the mth sample over the samples. So it is possible for me to say what is this expectation using these samples. So it is possible to use unnormalized samples, but there's always a caveat. The unnormalized method will work for some marginal probabilities that you're trying to compute. That is good news. But the unnormalized importance sampling is unsuitable for conditional probabilities. So for instance, p of x given e, so this is evidence. You're given a set of values. What is the probability of the other values? And with all of this argument here is that this causes serious errors, and if numerator is an underestimate, denominator is an overestimate, overall result is a severe underestimate. So just the unnormalized method runs into big divergence from where it should be. So so we go on to how to fix that problem. Is if we use the same set of, okay, it says use the same set of samples for both numerator and denominator, but it still has a bias issue and so on. And then the issue here is derivation of optimal Q star of X. So this is saying, how should you be choosing that Q? Now this brings in the notion of Kullback-Leibler divergence, which plays an important role in machine learning. Although here we're just talking about an optimal Q star of X. So this says any Monte Carlo estimator can be transformed into an importance sampling estimator. And says the variance of an importance sampling estimator is sensitive to the choice of Q. Right? So there is a certain sense of Q. So choice of suboptimal Q. Any choice of Q is valid and Q star is the optimal one. Sampling from Q star is usually infeasible. Other choices of Q can be feasible and reducing variance somewhat. So we can look for reducing variance. Obtaining the best possibility may be an issue. So there are a variety of methods here called biased importance sampling. And this we are using unnormalized samples again here, biased importance sampling. Unnormalized samples, P and Q. And this is again a discussion of choice of Q. Good Q means efficient Monte Carlo estimation. Poor choice of Q is efficiency is much worse. So it says the Q distribution is usually chosen to be very simple so that it's easy to sample from. So we could obtain a Q to be a simple version where the variables are all independent and so on. So that's called mean field inference, is using independence. So there's a rich topic here. Importance sampling is a method of using a proposal distribution, and the choice of the proposal is an issue, and some simpler version is used. And why do we need to know this? Is it is used in many machine learning algorithms, including deep learning. So the question is, where are they used? To accelerate training in neural language models with large vocabulary. Wow. So if you're going to be a language processing person, processing, whatever language you would like a deep learning network to process, to recognize, to understand, you'll find that it is needed to accelerate training of those methods. Important sampling is used. Estimate partition function, we just saw that issue. Estimate partition function Z, it is just a summation for a normalized probability distributions to normalize them, right? That's why we need the partition function. Without partition function, it's an unnormalized distribution. Or estimate log likelihood in deep directed models such as variation autoencoder. VAE is a very important method of generating samples, just like GAN, and we need to estimate log likelihood in these models. And finally, to estimate gradient in stochastic gradient descent, where most of the cost comes from a small number of misclassified samples. These last two slides show the equations of where importance sampling is used in a VAE. VAE is a method for generating samples in a complicated distribution, which brings in the Kullback-Leibler divergence to play a role here. And we generate samples from a normal distribution. So it's an encoder-decoder architecture, just like our autoencoder. Inputs X are encoded here, and that is used together with a sample from normal distribution 0, 1, and run through the decoder to generate a sample. So VAE is a very powerful method to generate samples, and to evaluate the goodness of a VAE, we decide to use Bayesian model comparison, the method of model given data, which model is better. For each model M, we need this quantity, and use importance sampling with Q being scaled and shifted Gaussians from our encoder. And so that is how it is determined, to determine the goodness of a particular model. So this was just an illustration that you want to determine how good your variational autoencoder for generating celebrity faces or what have you, bedroom scenes or churches. There are some examples people have done. So the goodness, you want to measure the goodness of the model. Give me a score so that I can compare this with another one. So this is called as a Bayesian model comparison. And you need samples from each model. And how do you get samples? It says get samples using importance sampling. And this last slide, I just was looking for where all is importance sampling used. This is an interesting example I came across, which is not quite a deep learning problem. It's got something like a Bayesian network here. A technique used in software development called PERT, Project Evaluation and Review Technique, PERT. This says that how long does it take you to develop some code? Planning, database design, module layout, database capture, database interface, input module, output module, GUI structure, IO interface, final testing. Okay. The predecessors, how long will they take? 1 week, and so on. And the duration of each of these, it says 4, 4. So what is the duration of each of these tasks? And perhaps the predecessor start time maybe. So there are predecessor values, duration values, and these are all being factored in. And so it says, here is your task. Planning is the first stage, and then you have database design and module layout here, and then database capture and so on. And 10 is when you get to final testing, everything has been put together. So if every task takes time shown in the table, then we are able to, and then there is a distribution associated with all of these. So none of these tasks is precisely fixed. It can take, plus or minus a certain amount of time. And so you want to generate a sample. So let's say you generate one sample from this and you want to show how long did this take, or we want to average over many times this was done, and we want to say, what's the expected amount of time for this project to finish. So it says importance sampling is the method that is used to get an estimate of the probability of what is the distribution. You can say, well, it's going to take me between 10 and 15 weeks to finish this project, and maybe the mean is 12, and the standard deviation is 2 or something like that. And how do you get samples? How did you get that value? Based on samples. How do you get the samples? Well, I got the structure here, and I use importance sampling to estimate it. And so then you have to work with some kind of proposal distribution for each of these variables, I suppose, or for the entire joint distribution, and then use that. All right. So that's the end of today's lecture on what are Monte Carlo methods and what is importance sampling. So we have one more lecture on Monte Carlo methods. Quickly revisit again Gibbs and others to put them into perspective. All right. Okay. That's all. I'll stop here. And if you have any technical questions, you can ask me.
Thank you, sir. It was a nice presentation.
All right. Thank you, Shelby. I'm going to stop at this point.
It was long time I wanted to study importance sampling because it's not part of our syllabus. We have not covered all these in our syllabus. So I've not studied at all. So
yeah, the thing is, sometimes when you're studying basic machine learning, they will give you 20 different sampling methods. So it becomes a very dull exposition of one after the other, and you don't know which ones you need to learn.
Correct. Yeah.
In deep learning context, I'm just saying, there are 2 things you must learn, or maybe 3 things you must learn. Ancestral, importance, and Gibbs.
Okay.
And so worth paying attention to what this is, right?
Yeah.
It's pretty intricate, but it's important to know this.
Yeah, it was really interesting and very nice procedure to understand. Thank you, sir.
All right, thank you.
Yeah.